Hi everyone. Induced EMF and current.
These principles provide guidelines for understanding the relationships between changing magnetic fields, induced EMF, and the resulting current. Let's go through a step-by-step process. Faraday's law. Faraday's law states that the magnitude of the induced EMF is proportional to the rate of change of magnetic flux through a circuit. Mathematically, this can be expressed as EMF is equal to negative number of turns in the coil multiplied by change in magnetic flux by change in time. Lenz's law. Lenz's law states that the direction of the induced EMF and resulting current is such that it opposes the change in magnetic flux that produced it. This law ensures that the conservation of energy is maintained. Direction of induced EMF and current. Change in magnetic flux. Identify the direction of the change in the magnetic field. This could be due to the movement of a magnet, the change in current in a neighboring coil, or any other factor causing the magnetic field to change. Apply Lenz's law. Once you have determined the direction of the changing magnetic field, use Lenz's law to figure out the direction of the induced EMF and current. If the changing magnetic field tries to expand, the induced current will create a magnetic field in the opposite direction to oppose the expansion. If the changing magnetic field tries to contract, the induced current will create a magnetic field in the same direction to oppose the contraction. Right hand rule. In many cases, you can use the right hand rule for induced current to determine the direction. If you point your thumb in the direction of the change in magnetic field, the curled fingers of your right hand will indicate the direction of the induced current. Lenz's law ensures that the induced effects oppose the change in the magnetic field to maintain energy conservation.
Let's discuss induced EMF. EMF is abbreviated as electromotive force. EMF is a force that is required for electron movement in a conductor. EMF is also known as voltage and its unit is the volt. EMF is generated from an electrical generator using Faraday's law of electromagnetic induction, figure 1. Faraday's law of electromagnetic induction states that whenever a current-carrying conductor cuts the magnetic field, a force is created in the conductor. This force is called an electromotive force or voltage, figure 2. This force will cause the current to flow through a conductor and then to the electrical load. The direction of the induced EMF can be determined by using the following procedures. Take a PVC pipe measuring 25 mm in diameter and 100 mm long. Wrap the PVC with super enameled copper wire 22 SWG for 600 turns evenly over the pipe, leaving some space at both ends. Fix the electromagnet or solenoid to the wooden boards with appropriate clamps. Remove the insulation at both ends of the enameled wire for 1 inch. Connect both ends to the galvanometer. Take a bar magnet and insert it in the hole of the pipe, like to and fro, to make electromagnetic induction and ensure the galvanometer movement. Ensure the galvanometer movement from the given table. Ensure the galvanometer stays in the 0 or center position. Insert the north pole of the bar magnet to the north side of the solenoid coil, wounded on the PVC pipe hole, and ensure the galvanometer and back to 0 position when the whole magnet bar is fully inserted. When you pull back the bar magnet to its original position, the galvanometer needle moves to the left hand side or negative side and then back to its original position when the bar magnet is fully removed from the coil. Now insert the south pole of the bar magnet to the south side of the solenoid coil and ensure the galvanometer needle moves to the left or negative side and then moves back to zero position while the magnet was fully inserted. When you remove the magnet from the coil, the galvanometer needle moves to the right side or positive side and then moves back to zero when the magnet is fully removed from the coil. Let us discuss how to determine the direction of current flow using a magnetic compass. Step 1. Take a super enameled copper wire of 22 SWG with length of 1 meter. At the center of the wire, make a 10-turn coil with equal distances between each turn. At both ends of the enameled copper wire, remove the insulation for 1 inch using appropriate tools. Take the magnetic compass and place it at the bottom of the coil turns. Connect a battery at both ends of the wire and remove the magnetic compass deflection. Now the current starts to flow from the positive terminal of the battery, which is also denoted by the plus sign. This causes the north pointing needle to point towards the left and the south pointing needle to point towards the right in the magnetic compass. Remove the battery and interchange its position so that the previous positive terminal is now negative and the negative terminal is now positive. Now the current starts to flow from the positive terminal of the battery, but current flow will be towards U, which is also denoted by the dot symbol. This causes the north pointing needle to point to the right and the south pointing needle to point to the left in the magnetic compass. From this video, I hope you can determine the direction of induced EMF and the current flowing in the current. Thank you for watching. You have a wonderful day.